In our introductory chapter regarding work and energy, there's one last topic that I want to bring up before we move on to the next chapter. This topic is power. Power is one of those words that we use in everyday life that has a little bit of a different meaning compared to when we use it in a scientific context. In everyday life, power, work, energy, we kind of conflate all of them, and we might use them interchangeably. Of course, in science and physics, these words have very distinct meanings. Work, of course, as we discussed, is like the total amount of effort to do a job. The total amount of effort expended on something to doing a job. We're changing the speed of this something, the potential energy of this something. We do work on it. We change its energy. That's how we define work. But power is the rate at which that work is done, the rate at which the energy of the object is changing. So it's like doing a job. Maybe you could do that job in 60 minutes. Maybe if you worked faster, you could do the same job in 10 minutes. Well, while you're doing the work, your power output during those 10 minutes is greater than the power output you would have if you were taking 60 minutes to do the job. So power is the level of exertion. It's the rate at which you are doing the work. So the faster you do the work, the greater the power output. Because it's a rate, it's basically calculated by taking the quantity work and dividing by time. That's how we generally do rates. If I want the rate at which something is moving, I take its distance or displacement and I divide it by time. If I want to know how the rate at which something is accelerating, I look at its velocity over time. So rates are just basically the thing you're looking at divided by time. Power is no different. But we're going to look at it in a slightly more generalized format. We are examining at how the energy of something is changing. So we redefine power to be equal to the change in energy over time. The kinetic energy is changing, the potential energy is changing. Whatever that change is, I divide by the time spent changing, and I have my power. It's not intended to be an overly complicated topic. You look at the total energy done, you divide by the time spent doing it, you got your power. Units for power are the same as units of energy divided by units of time. So it's equivalent to joules over seconds. And joules per second has been redefined to be the watt. This is exactly the same type of watt that you would find on a light bulb, a 60-watt light bulb or something like that. So this is one of the few instances where the metric measurement actually agrees with the everyday use of the device, everyday use of that measurement. One place where you see the use of the word watt would be a light bulb, but another place you might see it is on your electric bill. If you look at an electric bill, the energy used is in units of kilowatt hours. So you see watt there. The kilowatt hour is extremely literally named. Kilo, metric prefix meaning 1,000. A watt meaning a joule per second. An hour is 3,600 seconds. 60 seconds in a minute, 60 minutes in an hour is equivalent to 3,600 seconds in an hour. So a kilowatt hour is 1,000 times 1 joule per second times 3,600 seconds. And that winds up being 3,600,000 joules. 1 kilowatt hour is literally millions of joules of energy. To put things into context, though, on your electric bill, 1 kilowatt hour costs you about a dime. it varies, but 10 cents per kilowatt hour is not a very unreasonable estimate. Might be higher in some places at some times of day, but not a whole lot different from 10 cents per kilowatt hour. Okay. I want to move on to our new topic, our new chapter on momentum, and a word that I dislike, but it shows up in physics textbooks frequently, so I guess I got to give it some mention. Impulse. But think momentum. If you think momentum, you're going to get through this concept okay. What is momentum? Momentum is a bit like kinetic energy in that it depends upon mass and speed, but unlike kinetic energy, momentum has direction. Momentum, this is one of the simplest equations you're going to see this semester. Momentum, which is represented by a lowercase letter p, is equal to mass times velocity. That's it. P equals mv. But notice, velocity has that little half arrow symbol above it, representing the fact that it's a vector. Momentum has that little half arrow symbol above it. It is also a vector quantity. It has a magnitude and a direction. The direction of momentum is exactly the same as the direction of the velocity. Because it's a vector quantity, in this course we will have to worry about x components and y components. Momentum is proportional to the mass. Momentum is proportional to the speed. The magnitude of the momentum is proportional to the speed of the object. Momentum can we use the word momentum in everyday language. If we talk about a football game, we might say that a team that's on a roll, and we might say, well, they have a lot of momentum. And if you think about it in that context, what momentum represents is a trajectory, a measure of the trajectory and how hard it is to change it. So if a football team has a lot of momentum, the opposing team they're going to have to put out some seriously extra effort to change that course. Momentum is similar. If an object has a lot of momentum, I would have to exert a lot of force to significantly change its course. Units of momentum are the same as units of mass times units of velocity. So it's simply kilogram times meters per second. It does not have a special name. It is just kilograms times meters per second. Now, why are we introducing momentum? And there is something very fundamental associated with momentum. There's a similarity. In a way, it's like repeating Newton's second law of motion. But momentum comes with something special, and we're going to build up to that. But first, Newton's second law of motion was really originally based on the idea of momentum. We can see a little derivation backwards. Newton's second law, as we presented it in class, is that the net force equals mass times acceleration. Well, acceleration is change in velocity over time. So I have m times v final minus v initial over time. I distribute that m through these two terms, v final and v initial, and I get in my numerator m times v final minus m times v initial, with time in the denominator. M times v final, that's final momentum. M times v initial, that's the initial momentum. So my numerator becomes p final minus p initial. My denominator is still time. And final anything minus initial anything is the change in that anything. So an alternate way of expressing Newton's second law is that it's equal to change in momentum over time. And this is how Isaac Newton proposed his second law of motion way back in 1686 when he published his foundational work, the Principia. So, you know, that's nice, but big deal. We know Newton's second law of motion. Nevertheless, we're going to pursue this a little bit further. I can take that expression, force equals change in momentum over time, multiply both sides by time. I get that force times time equals change in momentum. This equation is called the impulse momentum theorem, which is an unreasonably foreboding name for a concept that is actually not bad. It says that if we want to change the momentum, then we need to apply a force over some duration t. Let's see if this idea, this equation is backed up by common sense. And I want you to consider a couple of questions. These are leading questions, I admit it, but I want you to get to an answer with which you feel comfortable. The first question. If I want to change the momentum of an object, if I want to see a significant change in its trajectory, do I want to apply a force that is weak or a force that is strong? A force of small magnitude or a force of large magnitude? Now, I'm not trying to trick you on this question. You should think, if I want to really change an object's momentum, I need a force of large magnitude. It's like having a bowling ball pass in front of you, and the difference between flicking it with your finger and giving it a good hard kick with your foot. Giving it that good hard kick is going to send it off on a radically different direction, whereas just kind of flicking it with your finger, you're not going to see any change at all. The other leading question, if I want to significantly change the momentum of an object, do I take this force and apply it for a small duration, a short duration, or do I want to apply it over a long duration? Again, this is not trying to trick you. Now, if you give a ball a light push, you're going to change its trajectory slightly. But if you keep pushing and pushing and pushing, even if it's a light push, if you push for long enough, you will change its trajectory significantly. And so that's all the impulse momentum theorem is saying. A large force changes an object's momentum more than a weak force, and application for a long duration is going to change the momentum more than application for a short duration. That's all the impulse momentum theorem is. Now let's apply this idea to this conceptual question. We have two carts, two wheeled things, and one of them has a mass of m and the other a mass of 2m. It has twice the mass of the first. Both start at rest. Don't ignore those two words, at rest. They start at rest on a frictionless surface, so we don't have to worry about friction. And we can also assume the surface is horizontal. We're going to push one cart for 3 seconds. We're going to push the second cart for 3 seconds. And the push on each cart will be exactly the same. The same strength force for the same duration for each cart. Remember that they start at rest. We apply the same force for the same time. What can we say about the momentum of the light cart afterwards compared to the momentum of the heavy cart afterwards? Does the light cart have 4 times the momentum? Is it twice the momentum? Is it the same momentum? Is it half the momentum? Or is it a fourth of the momentum of the heavier cart? Think about this, and if you have questions, this would be one of those questions to ask at the start of class when I ask, are there any questions before we get started? This next question, though, is a little bit trickier. I give you a hint, though. We're looking at the same situation as the previous example, but how does the kinetic energy of the lighter cart compare to the kinetic energy of the heavier cart? Is the kinetic energy of the light cart 4 times? Is it twice? Is it the same? Is it 1/2? Or is it 1/4? the kinetic energy of the heavier one. I'll give you a hint. There is a relationship between kinetic energy and the magnitude of the momentum. Kinetic energy is equal to the square of the magnitude of the momentum divided by 2m, where m is the mass of the object. Think about it. Remember the result from the previous slide. Think about it, how it affects the kinetic energy. And again, if you have a question, this is a great question to ask at the start of class. Let's do some numbers using the impulse momentum theorem. A 96-gram rubber ball bounces off of a wall. Maybe it's a racquetball, one of those little blue balls, a bit smaller than a tennis ball, bounces off the wall. And the speed it has before the bounce is 23.2 meters per second, and the speed afterwards is 18.2 meters per second. And the ball is in contact with the wall for 0.132 seconds, a brief period of time. What is the average force exerted by the wall on the ball during impact? Let's take a look at what's going on here. There's something subtle here. The ball bounces off of a wall. Visualize that. If you're visualizing it correctly, you would know that before the bounce, the ball is traveling in one direction, and after the bounce, the ball is traveling in the opposite direction. This has an impact on the value of the velocity. One of those velocities, we consider the velocity before the impact, the velocity after the impact. One of those velocities has to be positive. One of those velocities has to be negative. There's not enough information in this problem for you to decide which is which, but you've got to pick one to be positive and the other to be negative. So be careful. Visualize these situations. And subtle things like that are so easy to miss. Don't miss them. I chose that the initial velocity is negative. So perhaps it's traveling to the left and it bounces off the wall, and afterwards it's traveling to the right. So the initial velocity is negative 23.2 meters per second, and the final velocity is positive 18.2 meters per second. The mass of the ball in kilograms is 0.096 kilograms. I can calculate the initial and final momentum. 0.096 times negative 23.2 is negative 2.2272 kilograms times meters per second. The final momentum, 0.096 times 18.2, which is equal to 1.7472 kilograms times meters per second. Now, to use the impulse momentum theorem to get the force is equal to the change in momentum over time. The change in momentum final, 1.7472, minus the initial, negative 2.2272. I find that difference. It's the same as 1.7472 plus 2.2272. And I divide by the time of 0.132 seconds, and I calculated this to be 30.1 newtons. And to be more explicit, it would have to be 30.1 newtons to the right. So, okay, the impulse momentum theorem actually gave us a slightly quicker way of determining the force than the previous problem, but nothing dramatically so. What's the whole point? Why do we have this impulse? Why is momentum even involved in this course? And the answer is conservation of momentum. Yeah, I know what you're thinking. Oh boy. Yeah. Okay. I get it. But this is actually some foundational stuff here. This is one of the properties of the universe, conservation of momentum. So, because it is so foundational to our entire existence, it deserves mention. What do we mean by conservation of momentum? Conservation of momentum requires an interaction between two objects. So on the screen, we can have a sphere moving in one direction, a block moving in another direction, and they are going to interact with each other, and bam, they crash into each other. We can apply conservation of momentum to interactions between two objects. To understand this, as the block and the sphere get closer and closer, okay, nothing necessarily going on there. I'm not worried about any gravitational attraction between them. I'm worried about the force between them when they are in actual contact with each other. They are touching each other. The sphere touches the block touches the sphere, and they touch each other for exactly the same duration, exactly the same period of time, t. So the sphere affects the block for some period of time, t. The block affects the sphere for that same period of time, t. Furthermore, Newton's third law of motion. The sphere exerts a force on the block exerts a force on the sphere. Those forces are equal in magnitude and opposite in direction. These observations have consequences for momentum. We're going to look at the total momentum of the system. Momentum of object 1 plus momentum of object 2. So that's what we have here. We're going to specifically compare the momentum of the system before the impact, P initial, and we're going to compare it with the momentum of the system after impact, P final. Now, capital P initial, the total momentum of the system, and this capital P is not power. I am sorry that we are reusing the same letter. It's an annoyance, and I'm sorry about that, but here we are. The total momentum of the system, capital P initial, is equal to the initial momentum of the first object plus the initial momentum of the second object. And assuming the masses of each object doesn't change, that's M1 V1 initial plus M2 V2 initial. When the objects interact with each other, the momentum of object 1 is going to change, and the momentum of object 2 is going to change. The change in momentum for object 1, according to the impulse momentum theorem, is equal to the force that object 2 exerts on object 1 times the duration that the force is applied. And the change in momentum for object 2 is equal to the force that object 1 applies on object 2 for this duration of time. As we discussed, this duration is the same for both. Furthermore, Newton's third law says that the force that object 1 exerts on object 2 is equal in magnitude but opposite in direction to the force that object 2 exerts on object 1. So we see F1 on 2 equals minus F2 on 1. Making a substitution, I can say that the change in object 1's momentum is equal to the force of object 1 on object 2 times time. The change in object 2's momentum is minus the force of 1 on 2 times time. Equal to, what I'm trying to get at is that the change in momentum of object 2 is minus the change in momentum of object 1. They have the same magnitude for the change in momentum because they have the same magnitude of force acting on each of them over the same duration, but opposite signs because one of them is getting pushed to the left and the other is getting pushed to the right. The final momentum of the system, little p1 final plus little p2 final. If I wanted to subtract capital P final minus capital P initial, little p1 final plus little p2 final minus the sum of little p1 initial plus little p2 initial, and I can rewrite that. the change in momentum of the system is equal to P1 final minus P1 initial plus P2 final minus P2 initial. Well, P1 final minus P1 initial is the change in momentum for object 1. P2 final minus P2 initial is the change in momentum for object 2. And we established that delta P2 is equal but opposite to delta P1. So I could say that delta P2 is minus delta P1, and therefore delta P1 plus delta P2 is equal to delta P1 minus delta P1 equals 0. Final momentum of the system minus the initial momentum of the system equals 0. In other words, the final momentum of the system is equal to the initial momentum of the system. Now, if you didn't follow all of that derivation, that's okay. But the conclusion is important. The final momentum of the system equals the initial momentum of the system. I derived this formula assuming the masses stay constant. But even if the masses don't stay constant, if object 1 transfers mass to object 2, for instance, this concept still holds. The final momentum of the system equals the initial momentum of the system. This is assuming that there are no external forces acting on it. And that's why this applies to the universe. If we assume that there are no external forces acting on the universe, and we have no reason to think that there is at this point, the final momentum of the universe is equal to the initial momentum of the universe. So the total momentum of the universe is staying constant throughout its lifetime. Is that true? So far, the answer is yes. Although I'm talking about how it applies to the universe, though, I can apply it to the interaction of any two ordinary objects. And I can write this concept out in equation form. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And this equation is more useful than you might be thinking right now. Here's an example. We have a 1,500 kilogram car traveling at 23 meters per second. It collides head-on with an 8,750 kilogram truck traveling at 17 meters per second. These two vehicles just get totally mangled up together such that they have the same velocity. The wreckage, it's a single combined wreckage, so it has the same velocity immediately after the collision. What is that final velocity? This can be answered using conservation of momentum. We have enough information. We couldn't answer this directly using Newton's second law because there's no information about the duration of the collision. But I can find that final velocity. M1, 1,500 kilograms, V1 initial, 23 meters per second. M2, 8,750 kilograms, V2 initial, negative 17 meters per second. Where did that negative sign come from? Head-on collision. For there to be a head-on collision, they must be traveling in opposite directions. So, one of those velocities has to be negative. I just chose it to be that for the truck. We are told that the wreckage of the car and the truck all mangled together have the same final velocity. So there's a V1 final, there's a V2 final, but they're equal. I'm just going to call it V final. The initial momentum of the system is 1,500 times 23 plus 8,750 times negative 17. The final momentum of the system is 1,500 times V final plus 8,750 times V final. V final is the only unknown quantity, so we can solve for it. Turns out that V final is equal to negative 11.1 meters per second. We have the final velocity. I didn't know the duration of the collision. I couldn't calculate the acceleration. I can't calculate the forces, but nevertheless, I'm able to find the final velocity thanks to conservation of momentum. And the final velocity should make some sense. We have a car of 1,500 kilograms crashing into a truck of 8,750 kilograms. The truck is almost 6 times more massive than the car. And so the truck's velocity is not going to change as much as the car's velocity. Both of them will have the same change in momentum, but because the mass of the truck is so much more than that of the car, the velocity of the truck doesn't change as much as that of the car. And that's what we see. The truck goes from negative 17 meters per second to negative 11 meters per second, but the car goes from positive 23 meters per second to negative 11 meters per second. Before the collision, the car is traveling to the right at about 50 miles per hour, and after the collision, the car is traveling to the left at about 25 miles per hour. That's a big change for the car, but that's what we should expect in a collision like this. Without knowing the duration of the impact or anything like that, I can't do this using the second law of motion. And if I had given you the duration, it would have taken a lot more analysis and algebra to get to that same final answer. So conservation of momentum does allow for some cutting to the chase. It allows you to get some results very quickly. Take a look at this example, this conceptual question. A compact car, a small car, and a large truck collide head-on, and they stick together. Which vehicle undergoes the larger acceleration during the collision? The car, the truck, do they both have the same acceleration, or is there not enough information given? Think about it. Ask a question at the start of class if you're not sure. And bye-bye.